All right, recording is rolling. It is Friday, November 15th. All right, so just for context, we are a couple minutes into class. I just sent some juniors to the auditorium, so we got that. AP, here's a top scientist for that progress check that you guys just finished, the energy progress check. So yeah, awesome job if you made the list. Awesome job. Top scientist. All right, so a bunch of guys are hopping on Kahoot already. The pin is on the board. All right, so we're going to do a Kahoot on energy. Yeah, you guys AP, a lot of times I have to cut the Kahoot just because we got so many other things to cover, but I think today's a pretty good opportunity. All right. If we get some time, if we get about 10 minutes to the end of class, I want to do this poppers activity. If I can't fit that in, then I'll see if I can fit it in next week. But okay. All right, you guys just turned in your textbook puzzles. Speaking of textbook puzzles, I did get a question about one of those, so want to clarify something here just a minute. Yesterday, I gave you guys a take-home quiz. Does anybody not have the take-home quiz? Maybe it wasn't here yesterday. Oh, okay. Let me get you this take-home quiz right here. All right, everybody else got the take-home quiz, right? All right, so due on Monday. All right, that. All right, there's going to be an in-class quiz. Right now I have it slated on Tuesday, so let's have that as the default plan. I'll do a review with you guys on Monday. It's going to be mostly on forces, Newton's laws, a couple of projectiles, a couple of energy questions. You guys can bring in one paper for notes. And I'm also sort of planning on this to happen. I think we're probably going to have a hurricane on Wednesday, so we'll see about that. So you guys good so far? Good so far? All right. So before we get to the Kahoot, here I got a question about this number 24 on your textbook puzzles. So let's take a look at this one. You guys see this one with this weight and this M1, this M2, and the spring constant, right? Or the spring with the spring constant, right? Look at that. They're saying what's the maximum it's going to stretch, right? Best way to solve this is with conservation of energy. Here, so actually, here. So sum of energy initial equals sum of energy final. Okay. I'll show you another question later that maybe they could have asked that would be a different sub with a different answer. Okay. But you guys see this M1 here can fall some distance down. So isn't that supplying the gravitational potential energy? Right. So I'll call that like MGH. Right. That it can fall. It's going to fall down some distance. Okay. All right. Yeah. All right. Thanks. All right. All right. So that's going to lift this block M2. So this is M1 falling. Right. M2 is going to be lifted the same height, guys. This height's the same. Okay. Also, the spring's going to be stretched. So that's 1/2 k x squared. But instead of x, I could just call it h because it's stretched by amount that's equal to h. Isn't that the setup right there? Right. So then you could solve for h given everything else. Right. How far is it going to fall? Right. Guess that. Okay. Now, show you guys on the solutions. I wrote these solutions a few years ago, so yeah, I probably need to update this. So there's a few of these that I could probably write a little bit better, including this one. So I set it up this way. Guys, here's your MGH right here. I wrote that as MG negative D on the opposite side. I don't know why I did that, but it's mathematically the same. It still gets you the right answer, right? It's just saying like it's going to fall. Okay. Here's your MGD, the block being raised. Here's your 1/2 kx squared, the spring being stretched. I did throw in some kinetic energy terms, but then I pointed out that, well, the speed would be 0, so you could just ignore those anyway. Okay. All right, so a little bit different way to think of it. It still gets you the right answer. It's just, I don't know, probably need to update that. All right, so we got that. Oh, wait. All right, so back over here then. Guys, there is a different question they could have asked. I think I may have mentioned this briefly the other day too, which is what if it's not the maximal stretch? Because there's going to be some maximum stretch and it's going to oscillate back and forth for a while. And it's maybe eventually going to come to rest, possibly, right? Okay. Now, if there's a little bit of friction loss. What is that stretch distance at the equilibrium point? Is it the same thing as this maximum stretch distance? How many guys think it's the same thing? No, nobody say that. How many guys think it's going to be different? Yeah, it will be different. Now, how can you solve for the equilibrium stretch? You wouldn't use conservation of energy. You would use what method? like force equilibrium, right? So for that, I might say something like this M1 pulling down is balanced by a tension pulling up. So I got M1G down minus the tension force up goes to zero, right? That could be an equation, right? Okay. And then it's the same tension in the string that carries over here. And what's going on the right side? Well, I got the tension pulling up. So FT pulling up, right? Minus M2G is pulling down. And then the spring constant is also, the spring is also pulling down. But now if I'm subtracting, it looks like down is the negative direction. So I have to say minus because the spring is also pulling down. Guys, what's the spring force? Am I going to write 1/2 kx squared here? No, because that's an energy term. That has nothing to do. Ew. Force, 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 force. What's the spring force? What's that? Kx. Right. And then that could also be equal to zero equilibrium here. So I'll have the system of equations. You guys see a system of equations right here? I'll call it system. Okay. Now you could solve for this x, and that would be different than this maximum stretch that was called an H from before. Okay. It's two different things. Okay. All right. You guys can I get that? All right. All right. So hold on to that idea because I do have a poster for that next semester. I think you guys are going to say one about that. All right, so you guys ready for conceptual questions with Kahoot? I think we're ready for that. All right, let's get Kahoot going. Boing, boing. All right, oh, look at you guys go. In physics, work is defined as. Oh, yeah, force times distance, right? Push on some force, some distance. Right? Now, you guys know also the force and the distance have to be what, parallel or perpendicular to each other? Parallel, yeah. So it's just the components that are the same direction. Okay. All right. Got Sam, Jack, Emily, Hans, Alex. Points on the board. Nellie Newton pushes an object twice the force for twice the distance. She does. Twice the force, twice the distance.
4 times the
Force. One winner. One winner. Guys, you guys just said work is equal to force times distance, right? So if you double the force and you also double the distance, what's 2 times 2? 4, right? Right. Makes sense. Who got that? Fyodorovich. Whoa. Oh yeah.
No, I just generated a Russian name.
The unit for work. Better catch up to Fyodorovich, so I can stop saying Fyodorovich. Joules, yeah. All right, work, energy measured in joules. Oh, hey guys, what about food calories? Is that a form of energy?
That's kilocalories.
Yeah, or kilocalories. Yeah, that's also true. Yeah, food calories is 1,000 calories. Guys, what is a calorie? A calorie is how much energy?
1 gram of water, 100
There you go. 1 gram of water raised by 1 degree Celsius. Yeah. That's what it is. I want to say it's 4.18 joules. I think is what it is. Right. But it's a different way to measure energy. Suppose you pay a utility bill. Do you guys pay in kilowatt hours? Right. Hey, kilowatts. Is that like a power? Hours. Is that like a time? If you do power times time, that gives you an energy. Yeah. Ooh. Hector, Neela, Emily, Jack, Alec, Fyodorovich. Power is defined as all right. Work divided by time. Right? What's the rate of energy transfer? Work divided by time. Okay.
Yeah, that does sound.
I don't think the other red ones are anything.
I get that.
Okay. I got Luke, Jack, Hector, Eli, Hans, Emily. The unit for power.
Not a meter.
Watts. Watts. All right, let's go over all these. Guys, what does newtons quantify? A force. How about meters? A distance. Joules is energy or work. Yeah, and then powers in watts. Guys, 1 watt is one whatever what? Joule per second. Joule per second. Yeah. 1 joule per second is 1 watt. Got Luke, Emily, Jack, Hector, Eli. Hans on fire. The amount of potential energy possessed by an elevated object is equal to. We're done lifting it. Here, let's think in terms of formulas. Guys, what's a formula you guys know for potential energy? MGH is a good one. MGH. But guys, mg, could that be like a weight? And h could be like a distance. And the force to lift something would be equal to its weight times height. Yeah, so force times distance, that could be mg times h. You guys remember doing that in class, Dick? Right? Yeah. Right. Yeah, so force times distance, that could be mg times h. Also, that's the only one that makes sense in terms of units. Let's think in terms of units now. In terms of units, guys, what's the unit for energy? Joules. What's the unit for work? Joules. What's the unit for power? Watts. Force. Newtons. Distance. Meters. So there's only one possible answer, even in terms of units, right? Right. Right. All right. Luke, Emily, Jack, Hector, Eli, Hans. Kinetic energy is equal to. There you go. 1/2 mv squared. All right. You burn a gallon of gasoline, does work on your car, can bring up some speed according to 1/2 mv squared. Oh, yeah. How much further will a car traveling at 100 kilometers an hour skid to a stop compared to 50 kilometers an hour? So if you double the speed of the car, what happens to the braking distance?
Oh, I would like to double different.
Four times as far. 4 times as far. Is that right?
Okay,
Guys, if you double the distance of a car, it's going to skid 4 times as far, braking to a stop? Huh. How many guys remember this one right here? I think you guys have seen this one a few times now, right? Right. It showed up. Well, you guys seen this a few times, right? So I'm going to treat this as an open system consisting of only the car. Right. There's no hills. Don't have to worry about MGH. Right. So we say the car starts off with all 1/2 mv squared. And then minus work done by friction, force friction times stopping distance goes to 0 joules. Right. So it could set something like this, right? Hill substitution. Right? At the end, here's always this braking distance. And a really classic question in physics is to focus on this relationship right here. So if you double the speed, that factor of 2 squared is going to correspond to 4 times the braking distance, right? Right. Now that's in terms of proportions, but you could come up with any numbers you want. You can play it out. And if you double the distance of the car, it's going to be 4 times the braking distance. Oh, yeah. All right, guys, good. All right. Definitely a good one to be able to solve. I mean, that would be a really good free response question in May. Okay, I could give you that. All right, you got Jinza, Alec, Hector, Eli, Hans, Jack. Arrow in a bow has 70 joules of potential energy. How much kinetic energy will it have after it's been shot? Oh,
Wait, mid-flight or
sorry.
It's
70 joules, right? So the 70 joules and in the bow, maybe you could sort of think of like spring potential, sort of. Right? Yeah, it goes into the motion of the arrow. Set that equal to 1/2 mv squared. If you know the mass of the arrow, you can solve for how fast is the arrow going. Maybe something you could do. Got Emily, Jenza, Jack, Hector, Eli, Hans. As the pendulum swings back and forth. Ooh, remember Paul Hewitt about to smash his teeth out? Yeah, all the above. Right. So at the end points, it's definitely 100% potential energy because it has no motion, but it's all height, elevated height. Okay. Now, guys, this blue one here at the lowest part of the swing, it's all kinetic. That's really strictly true if you define the lowest point as zero height, which is the most convenient way to do it anyway. Right. Yeah, and so you get this oscillation back and forth between kinetic potential. Right. All right, pendulums. Got Emily, Jack, Jenza, Hector, Eli, Hans. When a car's speed triples, what happens to its kinetic energy? Formula for kinetic energy. That 1/2 mv squared. 1/2 mv squared. Yeah, 9 times the energy. Nine times the energy. Right. So you guys remember here, flip back over here. You guys remember this, right? Right. It's just this bit right here. Right. 3 times the speed is 9 times the energy. Right. And an extension question could be, therefore, what would happen to the braking distance? It would increase by a factor of also 9, right? 9 times the braking distance. Okay? If you go from 10 miles an hour to 30 miles an hour, you need 9 times the road. Okay? How about this? You take some gasoline to get your car up to, let's say, 20 miles an hour. Take some gasoline to go from rest to 20 miles an hour. Right? It also takes some gasoline to go from rest to 60 miles an hour, which is 3 times as fast, right? Right. Guys, how many times the gasoline does it take to triple the speed of the car? 9 times, because it's 9 times the energy. 9 times the gasoline, right? 9. Alec. Oh, look who's back. It's Fyodorovich. Jenza on fire. Hector, Eli, Hans, keeping that lead. Ooh. Job is done slowly. An identical job, say the same work, is done quickly. That's different amounts of, say it's the same mg, the same h, the same mgh.
Yeah.
Yeah, that's what I'm looking for. All right. Because when it says identical job, say you have to lift some weight, some height. So it's the same mg, the same h, that's the same mgh, takes the same amount of energy, the same number of joules, right? But power is work divided by time. So if you do a job quickly, guys, if you do a job quickly, is that more power or less power? More power, right? Because say if you took
More joules.
yeah, more joules per second, right? Say guys, say you did 100 joules in 2 seconds. How many watts is that? 50. Well, if you do 100 joules in 3 seconds, what is that? Like 33 watts, right? And since 50 watts is more than 33 watts, that took 2 seconds versus 3 seconds, right? Okay. All right. Yeah, if you're ever not quite sure, yeah, just jot some numbers down on your paper and kind of play it out. See what the practice work out. Fyodorovich, Jack, Jenza, Hector, Eli, Hans. Which requires more work? Lifting 70 kilograms up 2 meters or lifting 35 kilograms up 4 meters? Half the weight, double the height. Yeah, same work. So guys, the guiding formula is mgh, right? Mgh. So you have half the mass, but double the height. It's a wash. It's the same. Okay. Yeah, 4 times distance. Yeah. Yeah, there you go. All right. Fyodorovich, Jack, Jenza, Hector, Eli, Hans in the lead and on fire. Ooh, it's a close race for first. Trying to get first. Object that has kinetic energy. Oh, I might have to tell you guys this. No, take a guess. Take a guess. What do you think? All right. Yeah. Okay. Guys, if you look at the formula, guys, what's the formula for kinetic energy again? 1/2 mv squared. So the ingredients that go into that cake are mass and velocity, right? Mass and speed, right? Do you guys see? Look at this blue. We haven't talked about this blue one yet. I want to fit this in before the end of the semester. This will be the next topic. Momentum is mass times velocity, and we'll show that's also conserved, kind of like energy, right? You can do stuff with that. That's a vector quantity. But you guys notice it's like the same ingredients in the cake, right? It's just a different way of mixing them, right? Mass times velocity, right? Guys, acceleration is that a rate change of velocity, right? Which doesn't even matter what the mass is, right? And then a force. Okay, that doesn't matter about velocity either, right? Okay, so definitely a momentum, right? Same ingredients, different way of arranging them, different formulas, different ideas.
No way.
Fyodorovich, Jack, Jinza, Hector and Eli, Hans. Woo! 3 points behind. A pulley system can.
Yeah.
Oh. Okay. No. I guess tell you what, whoever picked the red one, here's how you could sort of technically be correct, is if maybe there was something you could not lift at all, but then maybe with the pulley system you can lift. And okay, then maybe the red one could kind of be right too. But yeah, definitely multiply your force, right? So you can increase your strength, gain mechanical advantage. You can of course change the direction, right? C is both of those, right? No, really what you cannot do is increase the amount of energy in total, right? Okay, so something like that. That's why it wasn't the red one. All right, Fyodorovich on fire. Jack, Jinza, Hans, Hector, and Eli taken first. How many joules of work done on the box? Force 25 newtons for 3 meters. All right, 75 joules. Force times distance. Fyodorovich, Jack, Jinza, Hans, Hector, and Eli. How much power to do 40 joules of work in 5 seconds? Uh, 8 watts, right? So 40 joules divided by 5 seconds, that'd be 8 joules per second, 8 watts, right? 8 watts. There you go. All right. Got Hector and Eli on fire. Oh, but still a race for first. What is that? Is that a 9-point gap? 9-point gap? Oh. How much work? 30 Newton crate lifted 2 meters. Got oh, hold on a minute. Is this not working? I don't know if my Zoom is failing right now. Hang on a minute. I don't know what just happened. How about this one? How about this one? All right, I think we're back. Okay, all right. So you guys go with that. Force times distance. Got 60 joules. All right, got Fyodorovich, Jinza, Jack, Hans, Hector, and Eli. Is this? Oh, we got 2 questions left. How much power? 60 Newton crate lifted 10 meters, all in 2 seconds. Yeah. All right, so 60 newtons lifted 10 meters. So that's 600 joules. Divide by 2 seconds, 300 watts.
Yeah.
All right. So force times distance divided by time. All right. Got Alec, Jinza, Jack, Hans, Hector, and Eli. It's a tight race. Tight race. All right, you guys ready for the win? For the win. A machine puts out 200 watts of power for every 1,000 watts input. What's the efficiency?
Whoa.
All right, 20%. Yesterday, I think you guys calculated efficiency a little bit different way. Guys, where'd the other 800 watts go?
Somewhere. Friction,
Good.
heat loss, a bunch of stuff that you don't want.
Yeah, there you go. All right, so AP could ask that question. I think that'd be a pretty solid answer right there, right? So friction, heat loss, that could be good. All right, podium. Hey, got with the bronze, Jack. With the silver, Hans. With the gold, Hector and Eli. All right, nice job. Nice job.
You see, my three there was right.
All right, you guys ready for poppers? All right, here. Oh, yeah, great. We got a perfect amount of time. You guys got a quarter page on your desk? Here, you guys see this on this quarter page. You guys got a quarter page lying around? Yeah. So it's kind of hard to tell. White paper on a white background. How about that? Huh? Do this way. Right, so guys, write your name on your paper. Name. And write Popper's Lab. Okay. Here's the question. How much energy in the popper? All right, looks like some Google grammar going on there, but I think that'll take care of it. So, you guys have seen these poppers? They look like little igloos, little domes. Right, I can fold this inside out. Right, put this down and pow! Whoa, went way up. You guys see how far that went? Oh, that's what you guys have meter sticks for. You guys got meter sticks. I just need to get you guys the poppers. Okay. Here, there is something you have to know to be able to answer this question. I'm gonna show you guys a really cool trick. You guys want to see a really cool trick? Because what maybe I'll ask you guys, what variables do you think you'd have to know to be able to answer this question?
The height, ring,
The
mass.
weight.
Yeah, okay. All right, so I hear Alex saying mass, right? Now there might be different ways you could possibly approach this, but be nice to know the mass, right? Nice to know the mass, right? Now I don't have a scale in this room, but here, this is a trick I've used over and over and over throughout the years, is you put down the fulcrum point, put down a ruler, and have this balance. There's one of the topics, probably in January, I have to show you guys, is something called torque. You guys have all played on the seesaw, right? Seesaw? I don't know, when I was a kid, we call them teeter-totters, whatever language, wherever I was in the country. So this could be like balanced like this. This is the same principle as how a triple beam balance is going to work. So I can take my unknown mass, I can put it on one side. Actually, I've got a couple, so this will make it more accurate. I'm going to get the mass of twice, or the weight of twice, and I'll just divide it by 2, right? I can put that somewhere. And then I can take a known weight, like this one's 10 grams. Guys, this is a little 10 grammer right here. That's the mass, a known mass. Okay. Now they're in the same gravity field, so the gravity field's going to cancel out. I could do this on the moon, and they would balance in the same positions, right? And I can put them on here so that it balances out. Now, right now, all right, do you guys see how this 10 grams pulls this whole thing clockwise like that? Okay.
Doesn't it also matter where you place them to?
It does. It does. Right. It matters where I place them. So what I can do is I can slide this around until it balances. See, I tried this morning. I think it was like right about here. Yeah, right about here. If I slide this around a little bit, just slide this. Right. Yeah. No, there's lots of places I could move this. I can't really move this out any further this way because I've run out of room on the roller here. Okay. But I can push this closer, and I can push these closer. I can do something like that. Let me just find one place where it balances. All right. Right. Okay. Yeah, I was having better luck with this morning. But probably right about here. Guys, if I shove this a tiny bit to the right, tiny bit to the left, it swings back the other way. Okay. So it's like right about here. Guys, what is the distance between 15 and 20 centimeters? What's that? That 5 centimeters? What's the distance between 15 and 1? Is that 14? 14? You guys see that? Okay. So next semester, I'll teach you guys about torque. Actually, I'll kind of show you guys right now basically what's going on. Okay. So from the side, it looked like this. Got fulcrum point at the 15 centimeter mark, that's like right at the center. Okay. And then here, I got 10 grams, so mass equals 10 grams. And this was 5 centimeters out this way, right? So D equals 5 centimeters. You guys see that? Okay. Then that's from this fulcrum point. Going to the left, distance, well, left equals 14 centimeters. Okay. I had 2 poppers, right? And I'll just call it, well, maybe I'll call it 2M, right? I'll call it 2M because there's 2 of them, right? But I don't know what that M is, right? Right. So this has a weight pulling straight down, and this has also a weight pulling down. Okay. So here's 10 grams times the gravity field of, well, 10 meters per second squared. Here's an unknown mass. I'll call it 2M because there's 2 poppers times Earth gravity field, right? And they're these distances. You guys see that? Okay. Now, I'm going to write down this word torque. So it's Greek letter tau, stands for torque. Okay. And you guys know something about equilibrium. You guys know equilibrium, all the forces have to zero out. You guys have known that, right? You have to zero out in the vertical direction and the horizontal direction for force equilibrium. Well, there's one more condition for equilibrium that I didn't tell you guys until right now, which is this torque also has to zero out. So what is torque? Torque is equal to R cross F. That's radial for distance crossed with the force, which at a glance might look kind of like energy because, hey, I see a force in distance. I just did a Kahoot. It's like a force in distance. This is a totally different concept because this is a cross product, and cross product you care about perpendicular components. So you guys see how like this radial distance to the left and this force are perpendicular to each other? Doesn't that make this whole thing want to turn counterclockwise like that? Okay. And this weight over here, oh, well, that's to the right of the pivot point. Here's my pivot point. Okay. So this makes it want to turn back clockwise. You guys see that? Right. And this left torque and this right torque, do you think they have to exactly zero out? Right. All we have to do is apply this little expression right here, and we can just zero this out. So it's going to go like this. I got, so R cross F. So it's 14 centimeters times 2M, and then G for Earth gravity. Okay. Because that could be the force, right? Okay. Minus this torque is equal to 0. So I'll just say equals and then slide this over. So that's over here. I got 5 centimeters. And that's a known mass of 10 grams. Notice I'm saying grams, not kilograms. Just be aware of that when you're doing this calculation later. And then also times Earth gravity. Earth gravity goes away. So if you do this on Mars, you get the same results. Right. So there's 5 times 10 is 50. Right, here, look, it's calculator time. Right, so 5 times 10 is 50. Divide by 14 and also 2. So 14 2 is 28. So divide that over. I'm getting 1.78. I'll round that to 1.8. So this M right here that I'm solving for, M for a single popper. Oh, whoops, I should actually divide that by 2. No, sorry, I did that already. Whoops. Right. Let's call it 1.8 grams. 1.8 grams. I think that looks about right. You guys think that one of these poppers is probably about 1.8 grams? Right, guys, yeah?
Yeah.
Right. Yeah, guys, several times over the years I've been teaching this class, there's been some object that's unknown mass, and it's like, oh man, if we just knew the mass of this, that would really be really helpful. And I've done this trick over and over and over. I've pulled out so many meter sticks and set up so many fulcrums, and it's really just a triple beam balance is what it is. Okay. Right, guys, yeah? Right, go ahead. You guys got the rest of the class? Now that you know the mass of one of these poppers. Oh, I need to get you guys the poppers. I'll get you guys the poppers. Figure this out right here. You guys got some meter sticks. Turn that into the gray tray, and that will be a close on the class.